Today we'll be continuing with where we left off in the last class. So in the last class we talked about actuators, and then I started discussion about a closed loop control system and the block diagrams. So I explained what is contained in a block and then what is a transfer function. So today we'll continue from there, and we'll see how to reduce different blocks in a control system and then to get one transfer function. Now the importance of that is that the denominator of the transfer function is the characteristic equation, and that determines a lot of things like stability, then the response of the system, etc. Okay, so it's very important that we understand how to do that and then proceed into controller design. So in the last class we started off talking about block diagrams, and we said that block diagrams essentially each block contains the transfer function of the system that is inside the block. For example, if this is a robot link, and we can represent this by a spring mass damper system. So inside here is my robot link, and this is one independent block, and many of these blocks in connection make up the complete closed loop transfer function. Now inside this would be the transfer function of the block. Now if we have a spring mass damper system, we can call it an MBK system. B stands for the damping, which is friction. So there is there's a force which can be applied, F. This is my position X, and this is K, this is B. So if I write my equation of motion, then it comes out to be mx double dot plus bx dot plus kx is equal to 0. Is equal to F. And if I take the Laplace transform of that, it becomes ms squared xs plus b s xs plus kxs is equal to f of s. From here, if I take my xs common, then what we get inside the brackets is ms squared plus bs plus k is equal to fs. Now if I consider this to be a block diagram like this, in which I have an input and I have an output. So my input is my fs. I'm applying a force to the block, because of which the block is moving, and my output here is xs. Then the transfer function is given as the output xs by the input fs, okay, which turns out to be equal to 1 by ms squared plus bs plus k, and this is called my characteristic equation. Okay, so now we understand what is the characteristic equation, and my characteristic equation will come inside here. Okay, so it will be ms squared plus bs plus k. Now the closed loop control system consists of a comparator, and a comparator essentially finds the error between the actual position and the desired position, okay, and then gives it forward to the controller. Now this is basically called a summing block, and this summing block essentially takes the signal and gives it back to the sensor and back to the controller. So in the feedback control system, which we are going to look at, so this is my feedback control system where we are going to look at, this point would correspond to, so these are the two blocks in the forward direction and the backward direction. This is my comparator block, and this is my feedback control system. Okay, so this is my GS and this is my HS. So the summing block here would be consisting of this one. Okay, now we also looked at what these blocks mean in terms of an equation. So if you have an equation like x3 is equal to this, then our control system diagram would be written in terms of blocks like this. Okay, now let us move further, and we saw reduction of control system diagram also. So we saw that the reduction of this closed loop control system would give you a transfer function, which is ys by rs is equal to gs by 1 plus gshs. Now please note this plus sign here and this minus sign here. Okay, so it is plus minus. Now if the feedback becomes a plus, then this will become a minus. Okay, so that is something to note. So please be careful about this signs here, which is plus and which is minus. Now we also derived how we got this transfer function, so please have a look at the last class. Now moving forward, a transfer function, a control system, the total block diagram would consist of multiple blocks. They would be consisting of motors, they'll be consisting of sensors, amplifiers, controllers, then other feed forward, feedback gains, and all of this has to be merged into one total function, in one total transfer function in the form of the output to the input. Okay, and then we'll look at the characteristic equation of that transfer function to talk about things like stability, etc. Now, so in order to merge these different blocks, what we need to do is combine these small blocks, and there are some standard ways of combining these blocks. Now, this is all what we call control system tradecraft. Okay, so control system engineers, they have devised these ways, and these are standard symbols that are used, and so please use this symbol. So G1 means transfer function of block containing G1, then this is G2. In the feedback direction we use the term H. So these are just standard ways of writing a control system. So now if there are two blocks which are in the same path, then we can simply multiply them like this. So G1 and G2 gets multiplied, becomes G1, G2. Now if there is a transfer block which is going in the forward direction, okay, so this one is going in this direction, okay, so in this case it becomes G1 plus minus G2, depending on whether this is plus or it is minus. Okay. Now this is the feedback control system which we are more going to be interested in. In the feedback control system, it is G by 1 plus or minus GH. So again, note this plus and minus there, so that will depend, so this sign here will be depending on that sign there. Okay, so it's a plus and a minus, then this becomes plus, and if it is a plus and a plus, then that becomes minus. Okay. Now moving further, we can use this reduction techniques to try and reduce a block diagram which contains many blocks. For example, this is an example. So there are many blocks. So G1 is there, G4, H1, G3, G2, H2. Okay, so these are all different blocks, and we need to bring it to one block because we want the transfer function of the complete system. So how do we reduce it? We start catching one loop at a time and then trying to reduce it by using one of this. Okay, so by using one of this, what we can do is we can catch one loop at a time and reduce it. So first, let's see, these two are on the same path, so I can simply multiply them, and that is my part 1. Okay, so G1, G4 becomes G1, G4. So this is the first thing that was done. Next is we have a look at this part. This is part 2. So what we can do is, this is going forward. So what we can do, this will become G1, this will become G3 plus G2, which is this one. Okay, now we have reduced this loop. Okay, now I need to reduce this loop, so this is my number 3. So third, I reduce this loop, this is a feedback loop, so this becomes G1, G4, 1 minus G1, G4 and H1. So there is a plus here, so this becomes a minus. Okay, and then after I reduce that, I finally reduce this fellow. This is my 4th, so this is my 4th loop which I'm going to reduce. And once I bring it to this form, okay, then you know what to do. This is GS and this is HS, so this is going to become 1 plus GS by 1 plus GS HS. Okay, so this is how I'm going to reduce my total. So this control system diagram has a lot of blocks connected in different ways. So I'm going to start reducing one by one, and then I'm going to bring it to one block only, such that I know the final transfer function output versus input. So all you need to do is to just refer to this and look at it. Now sometimes we may have to move blocks. Okay, so this is just for example. You can try it. For example, you can just reduce this one first, then reduce that one. Okay, and then multiply whatever you get here with with this block. That will be a total transfer function. Now sometimes we need to move the summing block, and we need to move the comparator block. So for example, we have a block here which is a comparator block from here to there. Okay, so in this case, what needs to be done is that the logic is whatever is the signal that is coming out originally. So whatever is the original signal here, okay, if I move the block from here to here, okay, the signal should remain the same. So what this means is, suppose this is my original and there was a signal which is XS here. Just for example, this is XS, this is YS, okay, and this is BS, just for example. Okay, so this XS signal which is coming out from there would be equal to YS minus BS, okay, into the block which is G. This is the original signal, okay, so which is equal to G into YS minus G into BS. Okay. Now suppose I shift this summing block forward. Okay, what would happen is here. So what is going to happen is I'm moving it forward. So I'm having my G here. Okay. I moved the summing block forward. This is my summing block now, and this is a signal here, and this is my feedback. Okay, so once I do that, what is going to happen is, let me draw it here. This is very clumsy here, so let me draw it at the bottom. So I'm drawing it here. Okay, so this is my G. Okay, and this is a signal coming in. I have moved the summing block forward now. Okay, and my feedback has come here now. Okay, so now we see that what is the signal that is coming out here. So this is my YS. Okay, so YS into GS will come here. So YS into GS will come here. Okay, at this point. Now what is the feedback from here? It is BS. So what is going to be the signal which is coming out of this? It is going to become YS YS into G, okay, minus BS. Okay, so I have just shifted the summing block forward. Now if you look at this signal, if you look at this one, and if you look at this one, you see that they are different now. So the logic being that you have to make some change in the circuit diagram such that the two signals become same. Now how do you make that same? So YSGS is there, so YSGS is here also, so that is okay. Here it is BSG, here it is only BS. So what we can do is we can put a G here. On this loop I put a G. Okay, the moment I put a G there, now this becomes into G, so it becomes YSG minus BSG, which is same as that signal. Okay, so that is the logic of how it is done. So if you move a summing block forward, like here, you need to add a G. Now if you move a summing block backward, like in the second case, what we are seeing here, you have to add a 1 by G. That means you have to remove the G. Okay, you can use the same logic and basically understand. So there is nothing to actually by heart here. All you need to see is use the logic, and it's very easy. Similarly, moving a takeoff point forward and moving a takeoff point back. Okay, you just have to add 1 by G and G. So by using the previous thing that we looked at, so by using this set of rules, okay, plus using this set of rules, okay, we can simplify any kind of block diagram and get a final transfer function. For example, this one looks very complicated, but it's not very difficult, because what we can do is we can start shifting. So I can shift this one here. Okay, let's take an example and see how it is done. So I shifted, at first I shift this summing block backward. Now if I shift it backward, what is going to happen is G1 and G2 will come in the same path. Okay, so I shifted it back, now we get G1, G2. I multiply these two, okay, and then proceed in that direction. So I multiply, it becomes G1, G2. Then what we do is you can complete this loop. Okay, this loop can be completed. Okay, so this is GS and that is HS. So it is 1 minus GSHS because it is plus here. Okay, so that way I can complete each of the blocks. Okay, I have combined one of the block and I've got this. Next, what we do is in the previous one, you see that there is one block here and there is a block here. So this is simple multiplication between these two, and what we get is this. Then I'm going to complete one block by maybe closing this one or closing that one. Okay, and getting it into one block. Then I'm going to close this one and I'm going to get one final transfer function. Okay, now this is one example of showing that even a very complicated looking set of block diagrams, okay, set of blocks like this looks rather complicated. Okay, you can actually manipulate by moving summing blocks and then closing loops, and then you can get the final transfer function. Now this is again something to remember here, is that we are talking about single input, single output. Okay, so what you see very clearly here is that there is only one input and there is one output. Okay, but we said that in a robotic system, very often, not very often, in a robotic system, we have two inputs. Okay, now what are those two inputs? This is my robotic link and this is my manipulator. Okay, now as far as the controller is considered, the controller only is controlling the motor. There's an encoder gear in front, so it's controlling the voltage to the motor. Okay, and the controller does not know what is the other things that is happening on any other joint. Okay, so this is what we call by independent joint control. But when the robot is moving, what is happening is that the velocities and accelerations are propagating. Okay, so if this link moves with a particular velocity, the second link is going to have its own velocity plus the velocity of the previous link, and this will start going forward. Okay, similarly, if there is a force there, this force will come backwards now. Okay, now because of this propagation, the effect of motion of any of the links has an effect on the forward links. Okay, so this means that, and this is basically what we get from our dynamic equations and from our dynamics. Now we know the dynamics will consist of inertia forces, Coriolis centrifugal force, and gravity forces. Okay, and the controller here, the independent joint control, has no way of knowing the dynamics of the system. Okay, it is just controlling the joint based on what is the desired position it has to go to. This is a position controller. Okay, and it doesn't know the dynamics, and there is no way of computing it. So what the dynamics does on the system is it starts disturbing it. Okay, so when it is trying, what this means is that if this, let's look at it here, this will make it very clear that we have a motor, we have a gear, we have an encoder. Okay, this link is moving, this one is moving, this link is not moving, this is not moving, it's fixed. But because this link is moving, an effect of that motion will come on this joint also. Okay, which the controller has no way of knowing. Okay, so this will act as a disturbance on the controller now. Now this means that you have two inputs. One input is the desired position you want to take it to, and the other is this dynamics fellow who is disturbing it. Okay, so in the case of a robotic link, we have two inputs, and the control system would look something like this, where you have, this is your desired position. Okay, so this is the position you want to take it to, and this is my, so this one is my position, and this is the dynamics. Okay, also called disturbance. Now you can see that this is a two input system. Now there is a position command which is coming from the controller, and or this is my desired position. So this is my desired position which is coming from here, and there is a disturbance which is coming from that side. So it's a two input system. Okay, so which is slightly different from the previous one we were looking at, which was only a single input and a single output. Now how do we solve this? How do we combine the block diagram in such cases? So in such cases we simply use the superposition of multiple inputs. We use this principle of superposition, which says that at any point you take one of the inputs, consider its effect, considering the other fellow to be 0. Okay, so in this particular case what we can do is, first we will say that R is there and U is equal to 0. Okay, so we get one transfer function. Then we get another transfer function where we say U is there and R is equal to 0, and then we add this plus this. Okay, that is what we mean by superposition, and by doing that you can get the transfer function of this two input system also. Okay, so determine the output C due to inputs U and R using the superposition method, which basically says that you consider one input at a time and simply add the transfer functions. So first, for this model we put U is equal to 0. That means we have only one input R, and we get the transfer function, which is very simple. We get a G1 G2 1 plus G1 G2. Next I assume that R is equal to 0, and I find the effect of U. Now something to note here is that there is a plus and a plus. Okay, so something to note in this there is a plus here and there is a plus there. Okay, so if I'm going to make R equal to 0, if I make R equal to 0, this input here is a minus. Okay, so I have to take that into account, and how do we take that into account is by introducing a minus 1 block there. Okay, so please note that when we make R equal to 0, because this is a minus here, so what we need to do is I need to put a minus 1 block here, which will make the input here minus, because that input was minus actually. Okay, so I do that again. It is very simple. So this is getting just simply multiplied by that, and then we close the loop. So if you close the loop, what you get is this one. So this gets multiplied by this, and then it's a GS by 1 minus GSHS transfer function. So what we get is this one. Okay, so basically what we do is so we get two transfer functions, and based on these transfer functions we are adding both of them. Okay, so look here a little bit. You should be careful about this minus, what is happening to the minus and what it is doing. Okay, so we are getting two transfer functions. Okay, so one is this, one is that by superposition, and this is the total transfer function of the system, which has two inputs. Now robotics applications comes under this, because we have two inputs. One is the desired position or velocity, and this is my dynamics. This is because of dynamics, also called disturbance. Okay, now this gives you a very simple way of understanding block diagrams and block diagram reduction. So we will be using this when we look as we go forward for the study of our design of controllers for controlling robot manipulators. Now as we proceed to linear control of manipulators, okay, so we are going to proceed to the next topic, which is linear control of manipulators. Now in this linear control of manipulators, we should understand that linear control techniques are valid. So when we say linear control technique, linear control of manipulators, linear control techniques are valid, okay, valid for systems which can be modeled using a linear differential equation. So valid for systems modeled as or modeled by linear differential equations. Okay, so this is something to note, that although we are saying linear control of manipulators and linear control systems are valid for systems modeled by linear differential equations, but robot manipulators are actually modeled by non-linear differential equations. Okay, so there are non-linear. Okay, so this is something to note. Okay, that although we are going to study linear control systems, but in reality robot manipulators are non-linear. They are modeled by non-linear differential equations. Now this is an interesting question again, that linear control systems are reasonable. They can reasonably approximate non-linear systems. Okay, so this is something to keep in mind, that although we are doing all this, we understand that robot manipulators are non-linear, but then linear control systems can reasonably approximate non-linear systems. Now why is something which we will look at as we go along, that this is reasonably approximating. Why reasonably? Because the errors, if the errors are very small, then we can get away by modeling them by linear control systems. Okay, now it's very interesting why the errors are very small and what you need to do to make the errors very small. Okay, now let's move forward and try and see what the controller should look like, and try and design such controllers. Now one way of trying to control the robot manipulator could be by using a trajectory generator. So we have a trajectory generator. You have studied trajectory generation. So the trajectory generator will generate angles theta d dot and theta d double dot. Okay, so trajectory is the time history of position, velocity and acceleration, and your trajectory generator can generate this. So we have a trajectory generator here which is going to generate, so this is a generator, and this is going to generate my angles theta d dot and theta d double dot. Okay, so this is now this is going to the control system of the robot. Okay, so this is my control system of the robot, and then finally the robot is moving. So the control system of the robot is generating the torques, the motor torque that is required, and it is giving it to the robot, and the robot is moving. Okay, this could be a scheme of controlling a robot manipulator. Okay, so whatever you have studied so far is being used in a trajectory generator, and then to generate the trajectories, give it to the controller. The controller uses the dynamic equations and to find the torque at the joint, and then it actuates the motor, actuates the motors, and the robot moves. Okay. Now it would appear that this scheme will work, but in reality this scheme will not work. Why? Because first of all, it's an open loop system. Okay, so this is an open loop system. So there is no comparison between the output, the desired, and the actual are not being compared. So this is open loop, so no comparison between desired and actual. Okay, now why is that required? Because the dynamic model is going to have, so the dynamic model will have errors. So the dynamics will be not very accurate. It will be an approximate model. Okay, plus lot of things are not modeled. For example, friction. friction, stiffness. Okay, all these things will start coming into picture, and whatever computed, the torque that you have computed based on your desired trajectory, this may not be correct. May not be correct, it will not be correct, it will not be exact. So what will happen is, this torque not being exact, the robot will not go exactly where it is supposed to go, it will go somewhere else. And because it is open loop, there is no way of understanding that, and there is no way of making any correction. Okay, so although this appears to be one way of controlling a robot manipulator, but this is a bad way of controlling a robot manipulator. You will not be able to control it. Okay, so what is done is that we need to use some kind of feedback. So open loop is not done, so feedback controller is made. Now feedback between what? So we can use different sensors that we studied, different position sensors, for example, and we are going to make a comparison between the desired theta and the theta and call it an error E. Okay, and if I take the derivative of this, then we can get theta dot minus theta dot is equal to E dot. Okay, now the control system, what it does is it can find these errors and it can make the error go to 0. So error going to 0 is what is done in a feedback control system. Okay, so what is done is we generate an error and then we try and make that error equal to 0 by using feedback, and this is the system that is followed, and this is the one that works. Now going forward, we are going to model each link. So I'm going to model the link via spring mass damper system. Okay, so which means that we are going to write our I'm going to model each of the joints by spring mass damper. Now there is the link has mass, that we know. There is some damping, there is friction at the joints, and it has some amount of stiffness. So all the more these links can be modeled by a spring mass damper system. And let me draw it here. So it is MBK. This is something you would have studied in high school maybe. Now this system, the equation of motion can be written in the form. So this is my x. Okay, starting x is from there. The equation of motion can be written in the form mx double dot plus bx dot plus k is equal to 0. Okay, now the solution of this equation, okay, is a time function of xt that specifies the motion of the block, and the solution depends on the initial conditions. So solution depends on initial conditions of position x and velocity x dot. Okay, so the solution of this is a time function of xt, and then we can get the solution once we know the initial conditions. So if I put a small force here, shift the x to some x, and I leave it, how it is going to behave will be determined by the values of m, b, and k. Okay, so now to study this system, what we do is we want to study the behavior of the system. Okay, what is the meaning of behavior of the system? It basically means that if I give it a small push and I leave it, how it is going to behave. Okay, so now what we do is we take the Laplace transform of this, which is equal to ms squared plus bs plus k is equal to 0. Okay, and we see that there are two roots. It has s1 and s2, which is equal to minus b by 2m plus minus root over b squared minus 4mk by 2m. Okay. Now from intuition, we understand that depending on the values of m, b, and k, okay, especially the values of b and k, the system is going to behave in a particular way. Okay, what do I mean by that? Suppose b is very large. Okay, b is large. Okay, that means friction is very, very large. So the behavior is going to be very sluggish. So if I give it a small push and I leave it, it is not going to oscillate much. It will just move a little bit and then come back. Okay, so it will be a very, very b is large. It will have very sluggish behavior. Okay, now this is just from intuition. So if I have no friction and we have a spring, and if I push it and leave it, it will just keep oscillating. Okay, so the values of b being very large or being very small determines how this is going to behave to some kind of disturbance, like if there is a force which is just pushing it and leaving it. Okay. So the solution of this equation tells us that there are two roots, and in the two roots there is a b squared minus 4mk under a square root. So essentially the system is going to behave depending on the values of b squared minus 4mk. Okay, and what are the three ways by which this fellow can behave? That is, the roots are real and equal. So roots are real, real and unequal. Okay, so this is the first case. What are the three cases? B squared is greater than 4mk, b squared is less than 4mk, and b squared is equal to 4mk. These are the three conditions only, right? So what we see for the first case is roots are real and unequal. This means that these are my roots and this is the response of the system. So we have two roots which are real. This is S1, S2. This is the real axis and this is the imaginary axis. Okay, and it basically means that this is my xt. So if I displace it and I leave it, what will happen? It will come like this and it will stop there. Okay, this is the meaning of real. Roots are real and unequal. Now, if I solve the equation, okay, in terms of x, what are we going to get? Xt is equal to, so which equation are we solving? This one I'm solving. Okay, in terms of I'm solving this equation in terms of xt as a time function of x. Then what are we getting is xt is equal to c1 e raised to s1t plus c2 e raised to s2t, where s1 and s2 are the roots that we just found. Okay, and c1 and c2 are the constants, and this can be found from the initial conditions. So initial conditions can be used to find, so for example, how far x was, initial condition in terms of x and x dot. So what was I displaced it to some distance x and then I left it with some velocity. Okay, so giving these two conditions I can find what is the values of c1 and c2. Okay, and when I solve it, this is my time axis, so what we'll find, the response will be something like this. Now there is another term which is used here, two terms rather. One is we have two roots, and these two roots are sometimes called the poles of the system. Okay, so these are also called the poles, and in terms of stability, it is known that if your poles are on the left of your imaginary axis, they are on this side, then the system is stable. Okay, if the poles go on the right of your imaginary axis, then the system becomes unstable. Okay, so another way of showing the stable unstable is what the poles, where the system poles are. So in this particular case, the two system poles are on the left side. Okay, and hence the system is stable. So this is telling us about the response of the system. It is also telling us about the stability of the system. What do we mean by stability of the system? Here basically we mean that if we give it a disturbance, it is going to go around and then come back somewhere near the origin. Okay, it may not come back exactly there, but it will come somewhere near there. Okay, it will not go off somewhere far off. That is what we mean by stable here. Now this is one where the roots are real and unequal. Okay. Now the next would be, now this is basically called an overdamped system. This is also called an overdamped system. The next case is if the roots are equal. So the second case we have is roots are equal. Okay, let's say roots are unequal. Okay. Now if the roots are equal, so if the roots are equal, then what happens is we get our solution of the form xt. So roots are equal, it is of the form xt is equal to c1 e raised to s1t plus c2t e raised to s2t. Okay, this is the form of the solution, and what we do get is the same thing if I draw here. Okay, now my response, I take it to xt. Okay, and I leave it. Now it comes, now it comes like this, and it comes very close to the, okay, so this is my response of the system. Okay, now what about in terms of the poles? So we have s1, s2, they are real and equal roots. Okay, and this is my imaginary axis, this is my real axis. Now because they are on the left side of your imaginary axis, they are still stable. Okay, and this is basically called a critically damped system. where b squared is equal to 4mk. Okay, so under this condition it is going to be critically damped and the roots are real and equal roots. Okay, so in most control system design we are going to assume that we'll make this assumption that the roots are critically damped. The system is critically damped and the roots are equal. Okay, now this is the second case. What about the third case? The third case is the case where we have complex roots. So this is the third case where we have complex roots, which means that b squared is less than 4mk. Okay. Now in the case of complex roots, the solution is of the form xt is equal to c1 e raised to s1t plus c2 e raised to s2t. Okay, but in this form s1 and s2 are complex, right? So we can also represent this by our standard we can represent such a system by our standard way of representing twice zeta omega ns plus omega n squared is equal to 0, where zeta is called the damping ratio, is equal to b by 2 km, and omega n is equal to root by kn. Now in terms of the poles and the response of the system, so I'm going to displace it by some xt, and then I'm going to leave it. So what will happen? It will oscillate a little bit. So it is going to come like this, it is going to oscillate a little bit, and then it will become steady like that. Okay, so this is my small oscillation, and then it is coming there. Okay, now this oscillating kind of behavior is when the roots are imaginary, and this is my s1 and s2, which are complex conjugates. So this is imaginary, this is real. Okay, so this is the third kind of behavior where we are finding that the system is oscillating in nature. Okay, now so these are the only three conditions that are there for a second order system that is represented by this equation. Okay, just depending on b squared is greater than 4mk, equal to 4mk, or less than 4mk. So depending on the values of m, b and k, the system is going to behave in a particular way. Now what way it is going to behave? Either it is going to be overdamped, it is going to be critically damped, or it is going to be underdamped. So this is an underdamped system. So which kind of performance do we want? Normally we would like the system to be critically damped. Okay, now this is how the system is going to behave naturally. Okay, that we have a mbk are the properties of the link, and if we just displace it a little bit and leave it, is going to behave like this. Now suppose if you are not satisfied with this natural response of the system, so not satisfied with the natural response of the system, and we want the system to behave in a different way. So not satisfied with natural response desired response, sorry, we are not satisfied with this natural response and we want the system to behave in some other way. Okay, we want the system to behave differently. Okay, in that case what we are going to do is we have to give an f such that the system behaves in the desired way. We want the system to behave in a desired way. So how do we get the system to behave in a desired way? We get it to behave in a desired way by giving an f, by giving a force to the spring mass damper system. Okay, so how do we give an f? So this f is given by an actuator. Okay, so the actuator applies a force, and now the system behaves in a particular way. Now if I write my equation of motion, mx double dot plus bx dot plus kx is equal to f now. So the question that comes up is what should be f? And essentially when we say control system design, basically we mean what should be the force that is given to the system so that it behaves in a particular way. In a robot link we are going to give a torque if it's rotating. If it's translating joint we are going to give a force. Okay, so this is essentially the question of control system design. What should be the input? What should be the force given to the system so that it behaves in a desired way? Now if we think a little bit, what should be the amount of force applied? Now it is from intuition we can guess that the force first of all should be proportional to the x. Okay, so if I want the system to behave and go in a long distance and keep it there, then basically I need to put the force should be proportional to the distance, which is equal to kp, a constant, into the distance x. Okay, now it should also be proportional to the velocity, okay, which is equal to kv into x dot. Okay, this is logical. Okay, so if I put only this one, what is going to happen is it is going to overshoot the point and it will start oscillating. Okay, so there should be something which is proportional or which should be changing with time, and that is basically my kv into x dot. So there is a change with respect to time. Okay, so if I put both of this in here, then what I get is mx double dot plus bx dot plus kx is equal to minus kp x minus kv into x dot. Okay, so the question was, what should be the f we are going to apply? And we said that we are going to apply an f which will be proportional to the force and should be proportional to the velocity. Okay, and if they are proportional, then it's equal to kp into x, and this is equal to kv into x, where kp and kv are called the proportional gain. This is called the proportional gain, and this is called the velocity gain, or the derivative gain. This is called the derivative gain. Okay. Now this is what we turn by a very simple PD controller. When we say PD, it is proportional plus derivative. Okay. Now in this equation, I can bring the kp and the kv on the left hand side. So we have mx double dot plus b plus kv into x dot plus k plus kp into x is equal to 0. Okay. Basically, I'm bringing it in the form mx double dot plus b dashed x dot plus k dashed x is equal to 0. Okay. So this part is my b dashed and this is my k dashed. Okay. Now we have brought it into this form. Now you understand again that the system is going to behave depending on the roots of the equation. So the whole idea is to bring it into this form because we want to know what it behaves like. So by putting different values of kp and kv, I can make it behave in a different way. Okay. Now so here what we are seeing is we have reduced our system to this form, and we want it to behave in a particular way. How do we want it to behave? So this is one equation, m x double dot plus b dashed x dot plus kx is equal to 0, k dashed x, and b dashed consists of kv plus b, and k dashed consists of k plus kp. Now you understand from here that this is one equation only, but there are two variables. One is kp is a variable, kv is a variable also. Okay, so there is nothing like what is the best value, what is the optimal value. Okay, so you have to basically tune the parameters. What does that mean? You put a value of kp, assume critical damping, and then see the response of the system. And if you're happy with that, then it's very good. If you're not happy with it, then you change the values. So this question of what is an optimal value of kp and kv, as far as this is considered, it may be optimal with respect to something. Okay, maybe overshoot, okay, rise time, fall time. But then this question actually doesn't have much meaning because you have one equation and two unknowns. You can just keep varying them and get particular responses. So when we say design of a control system, what do we basically mean for this particular case? That we are going to make some assumptions. First, we will say it is critically damped. Okay, so critical damping, we know that b dash is equal to 4m k dash. That's for condition 1, and I'll make an assumption that kp has some value, okay, some numerical value. Now with these two conditions, I'll be able to solve. Solve means find the values of the other variable kp. So I can find, once given kp, I can find kv. Okay. So that is how we basically design the control system. Now this is essentially a position regulator. Now what a position regulator does is essentially it maintains the position irrespective of a disturbance. So if the block is at some position and we disturb it, okay, it will try to keep it at that position irrespective of the disturbance. Okay, this is basically called a position regulator. It doesn't track any trajectory. Okay, it is just simply maintaining the block at a particular position. So it maintains a block at a desired position irrespective of disturbances. So irrespective of small disturbances. Okay, so this is the meaning of a position regulator, and what we have just designed is a position regulator. Now let's look at a very small example that will give you a better idea. So suppose we are designing a system in which our MBK, M is equal to B is equal to K, has values of 2 units. Okay, this is just for example. Now we want to design a position regulator. So it sounds interesting and fascinating to say design a position regulator. Okay, so we are designing a position regulator, which means find the value of Kp. So which means that we have to make some assumptions again, because you know there's one equation with 2 unknowns. So first equation we made, it is critically damped. Okay, so this is critically damped. And the second assumption we make, we take some value of Kp. So let's say we take equal to 16. Okay, so if I take these values, make this to assumption, then K dashed, our equation is mx double dot plus B dashed x plus K dashed is equal to 0. This is my equation, right? So in this case, B dashed or K dashed is equal to K plus Kp, which is equal to Kp. I'm making the assumption of 16 plus 2, which is equal to 18. Okay, so K was equal to 2. So what is B dashed? B dashed is equal to 2 by Mk dashed, okay, which is equal to, so B dash squared is equal to 4Mk dashed. So if I take B dashed, which is equal to 2 root Mk, which is equal to 2 into 12 into 18, which is equal to 12. Sorry, not 12, it is 2 Mk, sorry. Mass was equal to 2, so it is 2 square root of 2 into 18, which is equal to 12. Okay, now once we have got K dash, we have got B dash, we can find what is Kv. So Kv is equal to B dashed minus B, which is equal to 12 minus 2 is equal to 10. Okay, so we have got the value of Kp and we have got the value of Kv. Now what we can do is we can put it into this equation. So mx double dot plus B dashed was equal to 12 into x dot plus K dashed is equal to 18 is equal to 0. Okay, so we are putting it into this equation, and now what we can do is we can find the roots of this equation. Okay, now depending on whether the roots are real, unequal, it is critically damped. Okay, so this system is critically damped. That is the assumption we are making. Okay, so now we find the response of the system, that is, I take it to some point and I leave it. Suppose it comes like this, it oscillates like this and comes to rest, and we are happy with that. Then we say that okay, this is fine. But suppose it did not do that, and instead of doing that, it went like this and went very slowly, went there. Okay, then we are not happy with this. Then what you do is you can increase the Kp gain. Okay, so what the proportional gain does is it increases your how fast it is going to come back. Okay, so now if you want this to be the response of the system, okay, that is this is what is desired and you're happy with that. So the very question here is desired, and if you're happy with this, then your system is okay. Okay, your design system is okay. If not, then you change it. Okay, that is the only way. Now this is a position regulator, which basically means that it can only keep the position at a particular location subject to small disturbances. Now if I draw it, then it is going to be something like this. Okay, this is my system. In control systems we have to draw block diagrams always, because this gives you a pictorial representation and it becomes much easier to understand what's going on. Okay, so this is my kV, and there is a kp there, so both of these are going here and it comes here. Okay, so this is my f, so this is my x dot and this is my x. Okay. Now this symbol is also a comparator block, a comparator block of this form. Okay, it is exactly the same thing. Okay, so now we can see that this is my block diagram of a very simple position regulator system. Now some things to, as we move forward, this is at the simplest level. Now a couple of things that happen is in our system that we have made the assumption that we have drawn. Okay, and this system that we are trying to model here is making a lot of assumptions. That the first assumption it has made is that MBK are constants. Okay, so MBK are positive constants. Okay, now we know that especially the damping need not be a constant. Okay, spring stiffness also need not be a constant. It is constant only for a linear region, not otherwise. So now in a real system, what we are seeing is that this B and K need not be constants. Now if they are not constants, then we have to have some other way by which we can include the variation of this B and K parameters, or in fact any other parameter. Now that is what we do. Is in the next case what we do there is we partition this control system. So we call this control law partitioning. Now what we do in this control law partitioning is that we try to reduce this to the control of a single mass system, or of a unit mass system. We try to reduce this to reduce the system, reduce the control, reduce to the control of a unit mass system. So as far as the controller is considered, what we'll do is we'll try and break the control structure into two parts. One is the model part, which will take care of the model, which contains the MBK parameters, and the other is the servo part, which takes care of the KP and the KV. And how do we do that? Is essentially we say that the force that we are going to apply now will be consisting of two parts, alpha into F dash plus beta, where your alpha is equal to M and beta is equal to B into X dash plus KX. Okay, so this is our the substitution that we are making. So in my equation here, mx double dot plus bx dot plus kx is equal to f, and f is equal to alpha into f dashed plus beta. So if I put in the values, alpha was equal to m into f dashed plus beta is equal to bx dot plus kx. So what we can see here is that some of these terms are going to cancel each other. So this term and this term will cancel, this term and this term will go, and this term and this term will go. So what we are left with is that it is x double dot is equal to f dashed. So this is what we mean by control of a unit mass. Okay. Now how do we control this? So f dash, we make the assumption that f dashed is equal to minus kv into x dot minus kp into x. Okay, and we put it into this equation. So what we are going to get is x double dot, okay, is equal to minus kv into x dot minus kp into x, and from here what we get is x double dot minus plus kv into x dot plus kp into x is equal to 0. Now this is a unit mass system here. Again, we can assume this to be critically damped, and we can assume a value of kp, numerical value, then find the value of kv, find the response of the system, and if you are happy with it, very good. If you are not happy with it, you change the values. Okay, so there is no other way of designing this kind of control system. So this is the way it is done. Now let us look at what this control system diagram will look like. The control system diagram will look something like this. So we have the comparator block there, and then we have mass, we have another summing block, then we have the system, and now you'll appreciate why we did it like this. Okay. Now we are seeing that the control system is being partitioned into two parts. Okay. One part is the model part and the other part is the servo part. So the servo part is going on the left side. This is KB, so we are having it. Okay. Now one of it will come here and the other fellow is going to go there. Okay. So now this is my x dot, the feedback, and that's my x. Now what you can see from here is that this has been partitioned into two parts. Okay, the servo part is, the model part is here and the servo part is on the other side. This is the model part, which means that the MBK parameters, the MBK parameters are contained in the model part. It's my model, so the mass also goes this side. Okay, so this is my model part, which consists of the, so the model takes care of the M, B and K parameters, M, B and K parameters. So if there is anything nonlinear here, it will be taken care of in the model part, and the servo part simply deals with the KP and the KB. Okay, so this is basically what we mean by a partition control system. What are we partitioning? We have partitioned the total system into two parts, the servo part and the model part, such that if there is any variation here in the M, B or the K, it is taken care of in the model part itself, and whatever servo is going on, that is being taken care of here by KP and the KB, which are on this side. Okay, such controllers are called partition control systems. So these are called partitioned. Now again, something to remember is that this is still a position regulator, okay, but it can take care of a system in which there is variation of B and K parameters. But what we really want is a trajectory following system, trajectory follower. Okay, this is what we really want. Now, how is a trajectory follower made? A trajectory follower is made by creating a servo error. So we create a servo error and then we make the error go towards 0. Okay, that is how the trajectory following system works. Okay, so what we first do is we'll generate an error between desired and the present and try and make that error go to 0. So what is this error about? It is actual minus desired positions. Okay, and then we'll try and drive this towards 0 by putting a controller there. Okay, so today I think our time is almost up, so we will stop today, and in the next class we'll be taking up the trajectory following controllers, and then we'll move on to actual robot controller where we have two inputs, and we'll talk about design of PD and PID controllers for robot manipulators. So we'll stop here today. So thank you.